So let's look at the details of the Chapter 10 review questions. The first multiple choice. A study of road rage asked separate random samples of 596 men and 523 women about their behavior while driving. Based on their answer, each respondent was assigned a road rage score on a scale of 0 to 20. Are the conditions for performing a two-sample t-test satisfied? First thing you want to recognize here is this is a quantitative type of data because they're getting a numerical score. So it would be a t-test, and clearly it is two samples. Remember, we're going to check for random, independence, and normalcy for this. One thing to keep in mind, make sure that we do have random samples, and it is clear from here that randomness is met. As we see that we have random sample of both of those. For independence, we are always going to be checking is the population greater than or equal to 10 times the sample size. So for this case, our populations, we are looking for at least 5,960 men and 5,230 women. Make sure you do state that it would be appropriate and be applicable for independence. Then the test, because it is the means for our normalcy is n greater than or equal to 30 because we can use the central limit theorem. Clearly both samples are meeting that requirement. So yes, it does work. We have two independent samples and large enough sample sizes for the answer. Question 2. 35 people from a random sample of 125 workers from Company A admitted to using sick leave when they weren't really sick. 17 employees from a random sample of 68 workers from Company B admitted they had used sick leave when they weren't ill. A 95% confidence interval for the difference in the proportions of workers at the two companies who would admit to sick leave when they weren't ill is which one of these 5? So the first thing you want to decipher is this proportions or means. This is categorical data because did they use sick leave or not? So yes or no. So this is going to be a proportions test or confidence interval for this. The formula for the proportion is going to be our P1 hat minus P2 hat, which is our point statistic, plus or minus our critical value. In this case, we are using a Z. And then for our standard error in here, it's going to be P1 hat times 1 minus P1 hat, and that's over the sample size of the first one. And then we're going to add to it the proportion or the P hat of 2 minus 1 minus the P hat of 2 over its sample size of that number 2. Now, so then when you go back into here, we want to figure out what are the P hat values. The first one, it said 35 people from the sample of 125. And then the second one, we had a random sample of 17 employees from the sample of 68. So our sample sizes we can tell are going to be for N2 is 68. For N1, our sample size is 125, which all of these statistics do show. Careful for the P hat on this first one. The P hat of 1 is just going to be 35 over the 125, and P hat of 2 is going to be our 17 over 68, because those are the ones actually using a sick leave. And the respective percentages then are going to be a 28 for this one, and then for this one is the 0.25. The correct answer does end up being B for here, and you can just go ahead and double check. We're going to see the 28.25 in our correct sample sizes. The one thing you want to decipher though, which critical value are you going to use? To distinguish the critical value, this is a Z critical value, and this is for a confidence interval of 95%. So remember at 95%, to find the correct T critical or Z critical value for 95, we also have to include this tail, which is a 0.025. So then for the final calculation, it's going to be the inverse norm here of 0.975, 0, and 1, which will get you the 1.96. So that's how you decipher between the correct confidence intervals for this. Question 3. The power takeoff driveline on tractors used in agriculture is a potential serious hazard to operators of farm equipment. The drive line is covered by a shield in new tractors, but for a variety of reasons, the shield is often missing on older tractors. Two types of shields are the bolt-on and the flip-up. It is believed that the bolt-on shield was perceived as a nuisance by the operators and deliberately removed. But the flip-up shield is easily lifted for inspection and maintenance may be left in place. In a study initiated by the U.S. National Safety Council, random samples of older tractors with both types of shields were taken to see what proportions of shields were removed. Of 183 tractors designed to have bolt-on shields, 35 had been removed. Of the 136 tractors with flip shields, 15 were removed. We wish to perform a test of the two proportions are equal versus H sub A, we think that they're different, where PB and P of F are the proportions of tractors with the bolt-on and the flip-up shields removed. Which of the following conditions for performing the appropriate significance test is definitely not satisfied in this case? So as all tests, we're going to check for random, independence, and normalcy. The condition for randomness is clearly stated here, so we are good. For independence, let's check that the population is greater than or equal to 10 times the sample size. We clearly can assume that there should be at least 1,830 tractors with the bolt-on and at least 1,360 tractors with the shield up. So independence is fine. Now for normalcy, the significance test and the confidence interval actually has the same normalcy check. We're just checking to see if N1 times P hat of 1 and if N1 times 1 minus P hat of 1. And then if N2 times P hat of 2 and if N2 1 minus P hat of 2, all four of these have to be greater than or equal to 10. Now to check for our P hat 1, so P hat 1 we have 135 out of 183. And then if we take this and we times it by its sample space of 183, this is clearly going to be 35. So this condition is met. This other condition here, we are going to have the difference of 183 and 35. We have 148, so that's greater than or equal to 10. On the flip side, if we check for the other type, we had 15 were removed out of 136. So our P hat 2 is going to be 15 out of 136 is the proportion, times our sample of 136, so that is going to be 15. And then if we check the other one this last condition, that's going to get us at 121. So in this case, it looks as though all four sets are greater than or equal to 10, therefore it meets the approximately normal distribution. So when you look at that, you're going to be tempted to think all conditions are met. However, when it says here, look at the question, which of the following conditions for performing the significance test is definitely not satisfied? Well, it looks like all are met. So if we look at the options below, it's issues with the wording. Both samples chosen are at random, which we clearly do know that. So I'm going to eliminate that option. They are at random. The data come from two independent samples. Yes, we are good with that. I'm going to go to letter E. Both populations are at least 10 times the corresponding sample size. This is the same test for independence, so B and E really say the same thing. Now it comes down to A and D. D says the counts of successes and failures are large enough to use normal calculations. I would agree with that. That actually is met. We check the normal condition. Letter A has a couple of big issues with it. It says both populations are normally distributed. The first issue we do have is we wouldn't say it's normally distributed. We would say it's approximately normally distributed because we had to check the conditions for that. The other thing is not both populations, but what they're taking here is a sampling distribution. So the samples are normally distributed, not the populations. So this one has an issue for both of those reasons. Question 4, a quiz question gives random samples of size 10 observations from each two normally distributed populations. Tom uses a table of distribution critical values and 9 degrees of freedom to calculate a 95% confidence interval for the difference in the two population means. Janelle uses her calculator's two-sample t-interval with 16.87 degrees of freedom to compute the 95% confidence interval. Assume both students calculate the intervals correctly. Which of the following would be true? So if we look at it, Tom is actually using just our standard degrees of freedom and using the table, so sample size -1. Janelle, when you use the calculator is going to give you a more accurate degrees of freedom, where when you do it by hand, it's a conservative value. Here's what you want to keep in mind. Degrees of freedom is related to sample size, though. So as the degrees of freedom go down, so if degrees of freedom go down or are less, which is in Tom's case, what's going to happen is if the degrees of freedom go down, means we have a smaller sample size. A smaller sample size is going to have higher variability or higher standard deviation. And if you have a higher standard deviation or standard error, that's going to make your margin of error actually increase. So ultimately, it's going to cause the confidence interval to be wider. Again, a good connection with that is that smaller sample size, more variability. If there's more variability, things are going to spread out more. So spreading out more is going to be a higher confidence interval. Based on that, Tom's confidence interval would have to be wider because in theory, his degrees of freedom that's being used is more conservative or smaller. Now, the other answers here are kind of interesting to reflect on, though. Both confidence intervals, they are correctly done. You're going to have slightly different answers, but they're both adequate confidence intervals. And Janelle is not making a mistake by using her calculator. Again, the calculator is going to give you the more accurate degrees of freedom, where by hand it's more of a conservative one. Okay, question 5. A researcher wished to compare the average amount of time spent in extracurricular activities by high school students in a suburban school district with that in a school district to a large city. The researcher obtained an SRS of 60 high school students in the large suburban school and found the mean time spent on extracurricular activities per week to be about 6 hours with a standard deviation of 3 hours. The researcher also obtained an independent SRS of 40 high school students in a large school and found the mean time to be 5 hours with a standard deviation of 2. Suppose that the researcher decides to carry out a significance test where H sub O, the two means are equal, versus a two-sided alternative. And careful, the two-sided alternative, therefore, would be that H sub A, if it's two-sided, means that mu of the suburban is not equal to mu of the city. So what we're seeing here is we have a significance test of the difference of means. So you would want to look and see what your test statistics should be for that case. And now we do not know the standard deviation of the population, so we would use the T one, the T test. The statistic for that is going to be take the difference of your two means that you have for your samples, and then you're going to subtract that from the hypothesis of mean of 1 minus mean of 2. And then we're going to go over the standard deviation of 1. Remember, when you combine two variables, you have to take their variances, add them together to compute the standard deviation. So the standard deviation of the second squared over its sample size also. Looking at this formula, we know we can come up with the x bars for this. The value for x bar, the mean for this first one is going to be 6 hours, and for the next one it's 5. The mu, they are hypothesizing here, right, that they're the same, so there's no difference, so that would be 0, 0 minus 0. So on the top we are going to have the number 1. And then on the bottom, the standard deviation, we know for the first one, I believe was 3 hours, and that sample size was out of 60. And then here we have out of 5 hours, and that sample size was going to be out of 40. So when you do that, you can actually easily see, if you know the statistic formula, that would have to be letter B. Why do the other ones not work? Be careful. What they're doing in this one is they are adding the standard deviations together and then taking the square root of the standard deviations. You can't. You actually have to find the variances first and add them together. The flaw with letter C, again, is that they are doing, did not come in and take the square root of the bottom, so that's bad. This one here, again, they forgot to square both of the standard deviations. And then for the last one, letter E is actually a pretty good answer, but be careful. Letter E is calling it a Z statistic. This is calling it a T statistic. Because we do not know the standard deviation of the population, we are finding a T statistic for that. Other than that, they would have been treated in a very similar fashion. So be careful with the letters that you see being used. Now, question 6 is just piggybacking off of that, and it says here, if the p-value for the test is 0.048, a correct conclusion would be what? So remember, in our conclusion, we would say, in this case, assuming that we're going to use the alpha of 0.5, which is a really standard good one to use. In this case, p is less than alpha, so we would reject h sub o, and we are going to conclude h sub a. So to look back at what h sub a was, H sub A just said that the mean of a city is different from the mean of the suburban area. So the statement here that best reflects this answer It's first saying that we're going to reject H sub O. So based on that, we know that we could cross off A, B, and C. Which one of these last two best works? Is it best to say there is not convincing evidence of it, but we know that there is convincing evidence. So there is convincing evidence that there is a difference. So letter E is the best option in this case. Question 7. At a baseball game, 42 of 65 randomly selected people report owning an iPod. At a rock concert occurring at the same time across town, 34 of 52 randomly selected people report owning an iPod. A researcher wants to test the claim that the proportion of iPod owners at the two venues is different. A 90% confidence interval for the difference in population proportions is computed to be this. Which of the following gives the correct outcome of the researcher's test of the claim? So if you look at what the hypothesis test would have been if they had done a test, H sub O would have been that we're doing the population proportions here. So we would say P1 is equal to P2. However, what we really think, the hypothesis, we think P1 is different from P2. So that is what they're writing. Careful too, for the hypothesis, we're using the population parameters, not the statistics. For it to be different means that the answer, if we found the difference, would be something not equal to 0. So we're trying to see if the difference would not be equal to 0. Well, in this case, our best answer is going to be letter C. The reasoning is this. It says, since the confidence interval includes the number 0, so in here, the difference of being 0 is in there, the researcher cannot conclude the proportion of iPod owners of the two venues is different. And that's how you would use this confidence interval if you wanted to infer how would you address a hypothesis test. Again, because our population assumption of what we think is happening, the population actually did show up in our interval, so we can't say it's different. Question 8. An SRS of size 100 is taken from population A with a proportion of 0.8 of success. An independent SRS of size 400 is taken from population B with a proportion 0.5 of success. The sampling distribution for population A minus population B in sample proportions has what mean in standard deviation? Well, the one thing that we know for this is that the mean for the difference of the standard deviations is going to be the mu of, let's call it A minus B, is going to be equal to the p hat of A minus the p hat of B. Well, we know population of success was 0.8 minus 0.5, so we know that the mean of this distribution is 0.3. So from that, we can actually cross off D because we can't have a negative. Now the standard deviation, careful, we're just looking at combining these two, so we're finding the difference really of the two. Remember, for the difference, we're going to find the standard deviation or the spread. And in this case, we know the standard deviation is the same as the standard error from our confidence intervals. What we would do for that is p hat 1 times 1 minus p hat 1 over n of 1. We're going to add to it p hat 2 times 1 minus p hat 2 over the sample size of that. If we fill in the actual numbers with that, the numbers we would use would be 0.8, and then this would be 0.2 and 100. In the other one, it would be 0.3, and then 0.7, and then 400. And it's really irrelevant which one in this case for the standard deviation that I'm calling P1 versus P2. So I could have written these in different order. When you do that, you are going to get your mathematically simplified answer of 0.047. Based on that, this is the only one that meets that requirement of both the center and the spread being listed properly, which is C. And this is more of a review question of Chapter 7, finding the measures of center and measures of spread for the difference of two proportions. But it's incredibly related to what if we had to compute a confidence interval, we would use this basic information. Question 9, how much more effective is exercise and drug treatment than drug treatment alone at reducing the rate of heart attacks among men aged 65 and older? To find out, researchers perform a completely randomized experiment involving 1,000 healthy males of that age group. Half of the subjects are assigned to receive drug treatment only, while the other half are assigned regular exercise and to receive the drug treatment. The most appropriate inference method for answering the original research question is what? Would we do a test or an interval? Is it one sample, two sample? Is it proportions or means? If you think about the response that's going to come from this study, it's going to be yes or no, did it reduce it? So with that alone, it's going to be proportions based. Because we're doing proportions, we know that we are dealing with the p's. So it's either going to be this one or this one. It's not the means. Now, do you use, notice for the p's, they're only using z's, so we only do z critical value. Now the big question is, should we do an interval or a test for this? What the initial question is how much more effective is exercise over exercise and drug treatment? So to get how much more effective, I would actually want to get a numerical answer. The only thing that would give me information about the numerical answer would actually be the confidence interval itself. C is not a bad answer, but C would only allow me to say yes or no if there's a significant difference. It will not allow me to actually give a value of how much associated with it. Therefore, the interval is the most appropriate inference procedure to use for this case. Question 10. Researchers are interested in evaluating the effect of a natural product on reducing blood pressure. This will be done by comparing the mean reduction in blood pressure of a treatment of a natural product group and a placebo group using a two-sample t-test. The researchers would like to be able to detect whether the natural product reduces blood pressure by at least 7 points more on average than the placebo. If groups of size 50 are used in the experiment, a two-sample t-test using a significance level or alpha of 0.01 will have a power of 80% to detect a 7-point difference in mean blood pressure reduction. If the researchers want to be able to detect a 5-point difference instead, then the power of the test would what? Now, power can be difficult to understand, but let me start by doing this. I'm going to set up, assuming that the hypothesis was maybe that the mean of one is equal to the mean of the other. So if we do that, we're going to assume that the mu here was at 0. So this is our 0 difference. But they want to detect a difference of 7 points. So I'm going to say negative 7. So I'm going to come over here and I'm going to sketch my negative 7 being right here. Now let me explain to you why I put the curve there. If this is just a number line, if you think about it, if this is where 0 sits on the number line, right, negative 1, 2, 3, 4, 5, 6, negative 7 is going to bring me there. Now, how powerful is this test? Well, they're using a 1% alpha, so this is where alpha is. The power is actually going to be right here. This is how powerful this test is that we have. And here's what I mean. How powerful is the test if we assume mu of 1 is not equal to mu of the other, so the difference is 0? How powerful, if we use that test, is it to detect that there's a 7-point difference? This is actually an 80% bit of power, they said, so it's 80% powerful. Okay, so we understand that. I'm going to jot that here. This is the power, 80%. But they're like, well, what if we're not right? What if it's not a 7-point, we want a 5% difference, or 5-point? Fine. This is 0, 1, 2, 3, 4, 5 is going to be about right here. So I'm going to draw the new curve. 5% difference would be something about right here. That's negative 5. Well, let's continue my little alpha line, which would come down here. What happens to the power of this test? The power to detect it is going to be less than 80%. So in the picture, we can see that the answer would have to be letter A as the only option. If you are struggling with the concept of power, you are more than welcome to come and see me. I would think this is one of the more difficult concepts in this chapter. I will tell you what I have seen from the AP board, though. A lot of the questions they will ask you are more about sample size and how alpha changes the power. One thing I do want to highlight, though, as another kind of added bit of information, remember this right here, the alpha level, that's our type 1 error, whereas this over here is our type 2 error, and like I said over here, that was the power, is the relationship you're going to see amongst all of these curves. On to the free response. Question 10 or 11. Researchers wondered whether maintaining a patient's body temperature close to normal by heating the patient during surgery would affect wound infection rates. Patients were assigned at random to two groups. The normal thick group, where patients' core temperatures were maintained at a near normal of 36.5 degrees Celsius while with heating blankets. In the hypothermic group, where patients' core bodies were allowed to decrease to about 34.5 degrees Celsius. If keeping patients warm during surgery alters the chance of infection, patients in the two groups should have hospital stays of very different lengths. Here's a summary of the statistics on the hospital stays. So the normal thermic group, we had a sample size of 104, the mean stay standard deviation. The hypothermic, 96 is our sample, the mean and the standard deviation. Construct and interpret a 95% confidence interval for the difference of the true mean length of the hospital stays for normothermic and hypothermic patients. So when you're going to do this, remember, when they want you to do a confidence interval, you have to do state, plan, do, and conclude. I will tell you you can get away with not having to do the state portion, but you must show that you've checked the conditions. So you have to go through and you have to check for randomness. So for this one, if we take a look at it, patients were assigned randomly to two groups. So state, patients were assigned randomly. Just don't write the word random down. Put more than just that. Independence. For independence again, here we are checking for both samples that the population they chose from was at least 10 times the sample size. So show or state that there's at least 1,040 non-hypothermic patients to choose from, and then there's at least 960 of the hypothermic patients to choose from. Independence would have been met. Normalcy for this one, to be approximately normal. This is of the means, therefore, first thing we check, can we look at sample size greater than or equal to 30? We can in this case. So 104 and 96 are both greater than or equal to 30, so we can say that they are approximately normal. This is then going to allow us to be able to use normal CDF functionality. So those are plan conditions. The do conditions, there's not too much to have to do for this one. But let's write down the test. So we are doing, you must list the test name if you want to get credit or show the formula. The test name for this one, I'm going to write it down here. It's a 2 sample. We are doing a T interval. And we're doing the difference of the means. So now I've gotten credit for either writing the formula or stating the interval, and I just recommend stating the interval for this. If you were to write the formula for this one, if we take a look at what it is, our formula is going to be for the confidence interval is x bar 1 minus x bar 2 is our point estimate. We're doing plus or minus. This is a t critical value, not z critical value. We do not know the standard deviation of the population, so it must be t. And then the standard error is just going to be combining the two variables, so squaring the standard deviation, and then over at sample size, adding it to the other one so that we're computing its combined standard error. And basically, you're just going to pop in the values that they've given to us for all of this. We are going to have to find the t critical value, but we have, let's see, 12.1 minus the 14.7. is our point estimate, plus or minus. The t critical value, we'll come back and do that in just a second. Our standard error we're going to do here is 4.4 squared over 104. And then I'm going to do 6.5 squared over 96. Now I should define here which one that I'm doing. So we are doing the difference of the means of, back up to my vocab, it looks like for the writing, we're doing the normothermic minus the hypothermic, so in terms of which variable minus which. The t critical value for this one is we are trying to find a 95% confidence interval. So again, if we think back about that one, for 95% confidence interval, we know it's this range here is 95%, but we need the extra tail, so we need to capture 97.5% of it. The t critical value is right here. To find that, we're going to do inverse t of 0.975 of 0 and 1, and that will give us a t critical value of 1.985, which is where we're going to put right there. When you simplify this interval, what you're ultimately going to get is, our answer will look like negative 2.6 plus or minus the margin of error in this case, 1.5298. So again, we have our point estimate, we have the margin of error, which just means combining the critical value and the standard error together to get that. And then from there, you can write out the final interval. And in this case, what we're going to get is negative 4.162 to negative 1.038. Now, the conclusion part, I'm not going to write it. I'm going to say it, but you would have to say, we are 95% confident that the true difference between the mean hospital stay of the normothermic and hypothermic treatments is in between this range. Or another way, right, we're 95% confident that the interval of this right here includes the true difference between the two treatments of the hospital stays. Now, part B, does your interval in A suggest that keeping patients warm during surgery affects the average length of patients' hospital stays? So the question here, this is the confidence interval. If we had written a hypothesis test, we would have said basically that the mean difference of, I'll put normothermic is equal to that of hypothermic, but we really think it's different. So the hypothesis test would have said there's a difference, which basically means if there is no difference, it'd be 0. So is 0 within this interval? 0 is not within this interval, therefore, yes, there is convincing evidence that it does make a difference to keep the patients warmer during their surgery for better recovery time. So here we have question 12. A random sample of 100 of certain popular car models last year found that 20 had a certain minor defects in the brakes. A car company made an adjustment in the production process to try to reduce the proportion of cars with brake problems. A new random sample of 350 of this year's models found that 50 had the minor brake. Was the company's adjustment successful? Carry out an appropriate test to support your answer. So you are going to have to do state plan, do, and conclude. I already jotted down the hypothesis here, but so for the state portion, it's put together, but you have to actually define your variables. The hypothesis is that P1 minus P2, that there is no difference. And we're going to define on your paper that P1 is last year's model, P2 is this year's model, and the proportion of cars with brake issues. But we think that the hypothesis is that last year's model is going to be higher than this year's model, so the difference between P1 minus P2 should be greater than 0. And I'm choosing a 5% for my alpha or my confidence level. Now, we can do the plan portion. Let's start by naming that test. So this is the 2 sample. And we are going to be doing a Z test for difference in proportions. For difference in, P1 minus P2. And again, we'll define P1 and P2. Let's check for our random independence and normalcy. And you do have to write this down, so I'm just going to walk through it quickly here. Randomness, it says here they did take a random sample, so write that one down, that they did meet the random. And just don't put random, put they randomly took samples of cars. Independence, you have to check it for both of them. So we have that the population is at least 1,000 of cars to choose from for the first sample, and at least 3,500 for the second sample would be independent. For approximately normal, this is for proportions. So again, we're going to have to check the success of failures, and the proportions for successes and failures are met. They have to be at least both greater than or equal to 10. So in this case, if I do n times p, so we have 20 out of 100 times the sample size, so that would be 20, and then 80 for the other. For this one, we're going to have 50 out of 350 had the defects, times the sample size, so we're going to have 50, and then 300. So checking your conditions, all of these are greater than or equal to 10, so it's approximately normal. Now, for the do portion on this, I would just recommend using your calculator. When you go into your calculator, you're going to have to type in the various elements that they're looking for. You are going to select the 2 prop z-tests on the calculator, and it's going to ask you for the x1 values. So you have to find, x1 and n1, and then they want x2 and n2. And then we're doing, our test is going to be that P1 is less than, or in this case, I'm sorry, P1 is going to be greater than P2 is what we think for which one we select. In this case, what values do we put in for all of these? You should type in to your calculator what we have 20 for this one and 100. And then we're going to have 50 and 350 for here. And again, to mirror this H sub A hypothesis, our P1 is greater than P2 in this case. When you run that particular test, I recommend just jotting down some of the key elements from here. So the p-value, you're going to find that the p-value on this one from the calculator is going to be 0.08219. I would also write down, because we're doing the test, in the test we do look at the pooled proportion. So p hat pooled is 0.1556 from the calculator. And then I'll just put down the p hat 1. In this case is 0.1556, and the p hat 2 came down at 0.142857. Now that's all we need for the test. Everything is written that's required. So now let's make our conclusion. The conclusion for this one, we can jump right into it. In this case, P is greater than alpha, and I'm going to write 0.08219 is greater than 0.05. So we fail to reject H sub O, which means we cannot conclude H sub A. Now, you can't just say we cannot conclude H sub A. The best way to actually put this into words is just come back in here and say, we cannot conclude that the proportion of brake issues from the first one compared to the second is greater than 0. Just put it in context. So look back at H sub A, put this in words, and that's the best way to make your conclusion. Now, part B, describe a type 1 error and a type 2 error in this setting and give a possible consequence of each. So let's jump right into it. Type 1. Remember, for type 1, that means you reject H sub O when you should not have done so. So if we reject H sub O and conclude H sub A, means we do think there is a difference, and we would conclude that there are fewer defects. If we conclude there are fewer defects, people may believe that the cars are more safe and be more confident in driving them. So type 1 could be an issue with that. We might have more accidents than we'd expect. Now type 2, remember, we fail to reject H sub O and we cannot conclude H sub A, but it's wrong. So if that's the case, if we fail to reject H sub O and we conclude it, means we're going to say that the new brakes aren't working as well, or we didn't fix the issue when we really did fix the issue. So we're going to think we didn't fix it, so we're going to spend more money and try to fix it again, even though we've already improved it. So people will think that the new car has defects, but the new car doesn't have defects. They've been fixed, and so people may not actually buy the cars. Or the company may go back and put more money into trying to fix the defect when it really already has been fixed. Question 13. Pat wants to compare the costs of 1- and 2-bedroom apartments in the area of her college campus. She collects data at a random sample of 10 advertisements of each. The table below shows the rents in dollars per month for the selected apartments. So 1 versus 2. Pat wonders if 2-bedroom apartments rent for significantly more on average than 1-bedroom apartments. She decides to perform a test. H sub O, she says mu of 1 is equal to mu of 2, versus H sub A, mu of 1 is less than mu of 2, where mu of 1 and mu of 2 are the true mean rents of the 1-bedroom and 2-bedroom apartments, respectively. Name the appropriate tests and show the conditions for carrying this out. So we are dealing with the means here, and she's dealing with a 2 sample. So she is doing a 2 sample. First, decide if it's 1 or 2. It's for the means, and we do not know the standard deviation of the population, so it's a t-test for the difference in means. Now, random independence and normalcy. In terms of this, we clearly see that it is stated right here that she takes a random sample, so state the randomness. For independence, we can assume that there are at least 100 of 1-bedroom and 2-bedroom apartments for independence. And then for normalcy, this is for the means. So remember, for the means for normalcy are approximately normal if n is greater than or equal to 30. However, our sample size is only 10 in this case. When the sample size is only 10, what you have to do is graph out the data and look for no skewness and no obvious outliers. Remember, between 10 and 15, you can have some skewness and some a possible outlier. Anything less than 15, we're looking for no skewness and no obvious outliers. If you do sketch this, what I would recommend doing, I put this data in the calculator under list 1, and I made a box plot. And I did the same for the second bedrooms, and here's what my sketch looked like. Now, my picture may not be the best, but when you look at this, you really don't see any obvious outliers, and there might be a little bit of skewness in the 1-bedroom one here versus the 2-bedroom, and I should label those, by the way. If I was doing this on an actual exam, you want to have that labeled 1-bedroom versus the 2-bedroom. We need to know the difference. But then just go ahead and say there's no obvious skewness or no obvious outliers, therefore assume approximately normal. So basically, we have the state and the plan portion done. Now, part B, the appropriate test yields a p-value. So they did the do part for us. Interpret this p-value in context, and then state the conclusion. So the p-value, the definition, you do want to understand what this is. I could see this coming up as a multiple choice, is the probability that the statistic happens given that H sub O is true. So that's how you interpret a p-value. So in this case, what's the probability that the actual statistics that she got from the sample really happened, given the fact that H sub O is true? So if we look back at her test, the H sub O says there's no difference. So how likely is it, if there is no difference between these two apartments, that this statistic would actually happen? So here's how I would say it. Here's how I say it. There is a 5.8% chance that the difference in rents will be $78 or more. And here's where I got that from, by the way. The $78 or more, folks, came from the difference in this study. So I found just the difference in the two means. The first mean was 531 versus 609, so that's where I came that from. But again, there's a 5.8% chance that the difference in those two rents will be $78 or more, given that there's no difference in the two rents. So that's the likelihood of it happening. Fine. For part C, make a conclusion. And let's cover the three things. In this case, we're going to say P is greater than alpha, and we're going to show that 0.058 is greater than 0.05. Because of that, we fail to reject H sub O. And we cannot conclude H sub A, but let's put that in context. We cannot conclude there is a difference in the mean rents paid in a 1 to 2 bedroom apartments. Always put your conclusion in context. And sometimes people will struggle on what to actually say as this part of the conclusion. So we fail to reject H sub O. And again, if you say you cannot conclude H sub A, what I would do to put it in context is don't say cannot conclude H sub A. Come back and say we cannot conclude this, that the difference in the first apartment is less than the difference in the second apartment. You'd be just fine.